Welcome to all. So, today we will continue with our lecture, and now we will continue with the part 3 of the lecture. Okay. So, now we will be looking into a few energy absorbing elements, their behavior, their material compositions and how they absorb the energy. Okay. So, starting with the lecture. So, energy absorbing structural elements and materials. Okay. So, type of elements. So, element wise we have thin walled tubes, okay. We have thin walled tubes, So, we use thin walled tubes, we used sandwich panels, okay. We use corrugated sheets and we use cellular composite structures. Okay. So, thin walled tubes, they are normally used in case of this type of collapsing mechanisms. Okay. Sandwich panels, okay. Sandwich panels we have seen the panels having hard plates, then soft absorbing material and then hard plates. Okay. For let us say in examples of design of a bearing plates, okay, in which the hard metals is being sandwiched between the rubbers. Okay. Corrugated sheets have a great application. Corrugated sheets have a great application in term when we design for a W type of guardrail. Okay. So, corrugated sheets are extensively used in the transportation materials, okay, and cellular composite structures. Okay. For example, honeycomb type of structures. Okay. So, they have a high energy absorption capacities. Okay. For this thing we need to have a material selection also. So, metals we can select as the metals. Metals as we have seen, they have a very high energy absorption capacity, okay, and the type of metal to be chosen comes from this high plateau area. Okay. The metals which have large plateau, okay, it means that the force deformation area under this curve is large. So, this type of metals can be chosen as an energy absorption materials. Polymers and foams, okay, polyurethane and other high density foams also show this type of high density absorption. Okay. So, they can also be chosen as the energy absorption materials, and the composite type of materials. Okay. Materials having changing density or having different planes. Okay. So, this type of composites can be chosen as the energy absorption materials. Okay. So, elements that talk about the configurations and the materials that talk about the inherent material properties. Okay. So, combination of these two things will guide us into choosing an efficient energy absorption elements. Okay. Moving ahead. So, we will look into the cellular materials for energy absorption. Okay. So, cellular materials. So, cellular materials are nothing but they are solids made of pores or cell. Okay. Their unique combination of strength and lightness gives this excellent performance in the application requiring energy absorption, such as crash barrier or packaging. It means that they have a high EM. Okay. The value of EM is high, it means that the total energy absorbed per unit mass is very high. Okay. This is due to their lightness in the structure. Okay. So, some types of readily available cellular materials are honeycombs. Honeycombs are nothing but the regular 2D cells, 2D cell geometry, and most of the times they are hexagonal. The other type of cellular materials are foams. Okay. They are condensed 3D network things, and they have open and closed cell morphologies. Okay. Wood is also of an efficient energy absorbing material. So, it is a naturally occurring cellular material, okay, with anisotropic properties. Okay. And since the wood is lightweight, it also has high specific energy requirements. Okay. So, nowadays cellular textile composites have also come into pictures. Okay. So, these are fibrous modern materials and they are arranged in a regular cellular fashion. Okay. So, they also exhibit high energy absorption capacities. Okay. So, this is the honeycombings we have seen, foams, okay, wood and this type of cellular textile composites. Okay. So, here we can see different examples of the cellular materials which are used as an energy absorption materials, and their best criteria is that they have a combination of high energy absorption and they are very light. Okay. So, their EM value is high. So, they becomes a very efficient material in the energy absorption field. The stress strain behavior of cellular materials. Okay. So, the stages of stress strain response, it starts with the linear elastic range. Okay. So, what happens at the small strains? Okay. So, the cell wall tries to bend elastically. Okay. So, this is the cell wall bending range. Okay. Here, okay. In this phase the cell wall starts to bend. Okay. After that what happens? Okay. There is a prolonged stress in the system, the cell wall collapses and the energy starts to absorb. Okay. So, this is the plateau region. Okay. So, in the plateau region either elastic buckling will occur, plastic bending will occur or brittle fracture will occur. Okay. After that the densification starts. Okay. So, this is the main signature or the main property by which the cellular materials absorbs the energy. So, it has a sharply rising stress field, pore closes and there is a little compression. Okay. So, what happens is that there is a high densification occurring in this cellular materials. Okay. So, this gives rise to an efficient energy absorbing material. You can see that the area under this curve is very large. Okay. So, the total energy absorption capacity of this material is large. So, this is a typical stress strain curve for an honeycomb system. Okay. So, in this three region, the mechanism or the signature of the cellular solids is being defined. Okay. So, the signature composes of the linear elastic region, plateau region and the densification region. Okay. So, most energy absorbing applications exploit this plateau region where the material compressions are nearly constant stress. Okay. So, this region, okay, as we have seen clearly in the previous lecture and this lecture also. So, we always try to choose a material which has a higher plateau region. Okay. Moving ahead. So, honeycombs. So, earlier also we have seen honeycombs. So, we will try to look into a bit details. So, shell shape. So, it is primarily a hexagonal shape, but it can also be triangular core or any other shape. Materials, it is made of, it can be made up of metals, it can be made up of plastics, ceramics and other use. Okay. The main idea here is the geometry or the shell shapes, the regularized shell shape arranged, which gives the honeycomb its energy absorption capacity. Okay. So, industrial relevance. So, it is used as a lightweight core in sandwich structures for stiffness, insulation, crash worthiness. Okay. So, it has a very large applications across different industries. Okay. So, it has a very controlled geometry. So, the failure mechanism is stable, predictable and repeatable, and this makes them ideal for engineering analysis and applications needing predictable performance. Okay. So, the repeatability, the stable configuration, okay, makes this thing an ideal thing. And as far as the manufacturing is also goes, the manufacturing, installation and maintenance of this system is also very easy. Okay. It is cost effective and easy to do. Okay. So, that is why the honeycomb system has found its relevance in different applications. So, honeycomb geometry and relative density. So, this thing we have already seen in the previous examples. So, same thing has been iterated here also. Okay. So, again the similar type of behavior occurs for a honeycomb also. Okay. So, this is the similar explanation that we saw earlier also. So, we have seen the different phases of the behavior of the honeycomb. Okay. So, this is an aluminum honeycomb, okay, and from 0 to 7 we can see the different phases of the collapse in an honeycomb. Okay. So, mechanism governing deformation in honeycomb, the first stage the cell wall will bend locally, second stage elastic buckling will occur, plastic collapse will occur or brittle fracture will occur. Okay. So, this failure modes are at the cell level, buckling, plasticity or fracture directly determines real world energy absorption and reliability. Okay. So, the plateau stress controls the force during mean energy absorption stress, okay, and the densification strain, okay, strain at which the all void closes, okay, this is defined as the densification strain. Okay. So, the densification sets the maximum load and hence maximum energy that the cellular solid can absorb before behaving like a dense solid. Okay. So, densification is an important phenomena in case of honeycomb type of systems. So, now we look into the other material which are called as foams. Okay. So, foam has a different behavior than the honeycomb structures. So, in contrast to the honeycombs where the cells are two dimensional, cellular materials, these are the cellular materials with three dimensional cells, and this three dimensional cell configuration is called foam. Okay. So, it has a cellular structure, it is three dimensional. Okay. So, it has a open cell structure. Okay. When in an open cell structure, when cells are connected by beam type edges only, that is fluid can flow among the cells. Okay. There is something called a closed cell configuration also. In the closed cell configuration, what happens is that when a cell is fully enclosed with cell walls, so that there is no passage for a fluid to flow among these cells. Okay. So, this cells in an open cell, the flow of the fluid will be allowed, and in this closed cell there will not be any flow of the fluid allowed. Okay. So, here we can see an example of an open cell left. Okay. So, the open cell, so this is given by a polyurethane layer. Okay. So, here you can make out that there are openings out here, okay, from where the fluid can flow, and there is another configuration polyethylene foams where you can see that this is a closed cell configuration. Okay. So, here no fluid movement is applicable. Okay. So, this is an open cell configuration which allows the movement of the fluid flow, and this is the closed cell configuration which does not allow the movement of the fluid flow. Okay. So, for an open cell foams, okay, the relative density is defined, okay, and the definition of the relative density for the closed cell foams. Okay. And C2 and C3 are the constants. Okay. So, depending upon the shell shapes, this constants will be given. Okay. So, stress strain relationships of a foam. Okay. So, it has a similar shape to the honeycombs. It is linear plastic plateau and then densification, linear plastic, linear elastic, then plateau formation, and after that the densification will occur. Okay. So, if the foam has higher density, then it will have a higher modulus and higher plateau stress, and it will have an earlier densification. Okay. Okay. So, densification strain for both open and cell foam is given by this equation. Okay. So, very low density foam can compress a lot before stiffening, high density foam reaches the end of their plateau much sooner. Okay. So, it is advisable to use a low density foam, okay, to achieve more densification. So, after that we give an example of a metallic foam. So, metallic foam has also emerged in this recent past, and they have emerged as a new class of materials with great potential as energy absorption structures and among other applications. So, normally the metal foams are made up of aluminum or nickel. Okay. So, this is an example of a metallic foam which has undergone the impact. Okay. So, as we can see for any other material, okay, here the elastic phase is there, after that the plateau region occurs, and even after the plateau region the densification region is occurring. Okay. So, a peak or plateau stress which is very high will cause damage to the goods in their packing or severe injuries to the passengers in the vehicles. Hence, for a practical application, so practically use this metallic foams, the maximum allowable stress specified, a metal foam with the best specific energy absorption should be selected. Okay. So, here the energy absorption which has a high specific energy absorption criteria, okay, which has a high EM criteria should be used. Okay. Moving ahead. So, wood, so this is the characteristic of a wood. So, wood is also used as a natural cellular material, and it is also very efficient for the energy absorption. So, it has orthotropic planes, radial, tangential and axial, and its microstructure along the axial direction is very different from that of the other two planes. Okay. So, this is the microstructure of a commonly used wood, that is cedar, is being shown out here. Okay. So, this is the typical stress strain curve for wood. Okay. So, wood exhibit general characteristics of a stress strain curve that is similar to honeycombs and foam as discussed earlier. Okay. Initial peak stress is present when compressed in the axial direction. Okay. So, initial peak stress is present out here. Okay. The axial collapse mechanisms is very complicated in case of wood. Okay. So, normally what we do is that most woods are of high density and plastic yielding. Okay. They are of high density and the plastic yielding will occur first. Okay. So, the collapse mechanism in the radial and tangential direction is largely dominated by the plastic bending of the cell walls. Okay. So, this is how a wood as an energy absorbing materials will behave. Okay. Moving ahead. So, now we come to the cellular textiles or composites. Okay. So, the cellular textile composites are nothing but they are regular grid domed textile composites. Okay. And they are fabrically woven into a 3D dome structure, cone structure or a hardened type of structure. Okay. So, it can be a dome and a conical wall structure, it can be a flat topped cone only structure. Okay. So, these are the different configuration of a cellular textiles. Okay. So, when compared to the conventional materials, okay, this new class of cellular textiles have a higher specific energy capacity. Okay. So, this is what it makes them comparable to the conventional ones and even sometimes better than the conventional one. Okay. It has a more stable deformation mode. Okay. So, the stable deformation mode is here, okay, which was our requirement for choosing a better energy absorbing materials, and it has almost constant force magnitude during the large deformation process. Okay. So, this is the requirement for our having our R max versus R naught comparable. Okay. And it has also a large deformation phase. Okay. It means that the stroke is more. Okay. So, if we looked into this material, it ticks all our criteria. Okay. Energy, it has a higher specific energy, okay, stable deformation mode, okay, constant fold, R max and R naught are comparable and large stroke. Okay. So, all of our requirements are being fulfilled out here. Okay. So, due to its all these great features, okay, this class of composites has found application as energy absorbing liner of various safety helmets. Okay. So, since these are soft materials, so they are used as a liners in different types of helmets, okay, in cyclist helmet, motorbike helmet and other energy sports. Okay. So, this energy absorption criteria combined with their repeatability, manufacturing, installation is in manufacturing and installation, they have found great applications in the field of sports protective wear. Okay. Next is the sandwich composite structures. So, sandwich composite structures we have seen they are nothing but there are two phase sheets separated by a lightweight thick core, okay, such as foams or any other honeycombs. Okay. So, this is nothing but a combination of the two layers. Okay. This is the soft layer and this is the hard layer. Hard layer is normally used to distribute the energy over an greater area and the soft layer is used to absorb the energy. Okay. So, this type of configurations, okay, where this type of things are being used, okay, the sandwich configuration. So, they have found application in case of blast applications, they have found application in case of vehicle crashworthiness. These panels are also used as face sheets in many applications, and even when there is a case of penetration, okay, due to projectiles, this type of a two layered approach is being used as an energy absorbing material. Cellular foam structures, we have already seen the foam type of configuration, open configuration, closed configuration. Okay. So, the foam sandwich structures, again this foam can be used as a sandwich structures also, okay, and it has an application in performations, shock waves, crashworthiness and other applications. Okay. So, using the materials or the materials by themselves or using them in a sandwich configuration can have an efficient application in different fields, like across the blast field, impact, crashworthiness, protective helmets, gears and other fields. So, nowadays new class of materials is also coming up, they are called the architected core structure. Okay. So, what happens is that the non-uniformity of the cell structure of the foam due to the existing fabrication process, okay, results in a lack of efficiency in mass production. Okay. So, due to the enhancement in the manufacturing technologies such as 3D printing, this type of architected core structures have come into limelight. Okay. So, they are nothing but the engineered geometries. Okay. So, different type of engineered geometries are being used to have an efficient energy absorption criteria. Okay. So, this type of different type of energy engineered systems are being used for an efficient application. Okay. Lattice like structure are being used. Okay. So, what happens is that due to this 3D printing, okay, we can print any configuration, this type of configuration can be printed and this type of configuration can be used. Okay. So, instead of a regular honeycomb geometry or any other geometry, this type of geometries can be printed, optimized and can be used as a different type of application. So, different type of lattice or truss type of structures can be used, okay, and they can be manufactured in a regular fashion. Okay. So, this type of things are finding new applications in the field nowadays. So, again the origami or folded type of structures, okay, they are the same continuation of the again the engineered materials. Auxetic materials or metastructure code. Okay. So, auxetic materials. So, we have dealt with the auxetic materials also. So, the auxetic materials, they have a negative Poisson's ratio. Okay. So, this is the key factor of the auxetic materials. Okay. They have a negative Poisson's ratio and they are finding a large application in case of the blast and impact resistance. Okay. And they can be easily 3D printed, okay, and they have an application across different fields. Okay. So, tubular core like structure. So, they can be used as a sandwich panel, okay, because they have a very regulated collapse mechanism, okay, and this type of stable collapse mechanism can result into an efficient materials, and when sandwiched with different face plates, they can again be easily used as a energy absorbing materials. Okay. Corrugated core like of structure, again corrugated cores are conventionally used for as a guard plates and all in the transportation applications, and they can also be sandwiched between these sheets and can be used as an efficient energy absorbing materials. Okay. So, here we have looked into different type of energy absorbing materials, we have looked into the conventional absorbing energy materials, okay, and then we have looked into the application of this conventional energy absorbing materials by combining them with the hard face sheets. Then we looked into the newer materials where the 3D printing is coming into pictures, where truss or other lattice type of things can be regularly printed and they can be used as an energy absorbing materials. After that, we looked into the auxetic materials where negative Poisson's ratio materials can be used as an efficient energy absorbing materials. Okay. So, we have looked into different plethora of energy absorbing materials and combining their properties. Okay. We can always design the best energy absorption system for our practical applications. So, I encourage you to go through the examples that have been given and make a case study where we take up a real life problem and apply the different systems and see which one is the best system that can gives us a good result. Thank you for today.